Stefan Hajnoczi. I'm going to talk about security in QEMUs. Let's get started. Okay, so just a little bit about me. I work in Red Hat's virtualization team, and I've been contributing to QEMU since around 2010. And over those years, I've been involved in reviewing security fixes and also in the disclosure process. We haven't really had a talk at KVM Forum that gives an overview of QEMU security issues, a bit about the design of how things work, both some information for users who are deploying it or considering QEMU, as well as for developers, what to look out for when adding new features in order to keep QEMU secure. Okay, so let's start off with the security process. There is a security process for reporting security issues to the QEMU community. And the whole point of that, like most disclosure processes, is that if a security bug is discovered, it's important that that bug remains private and not publicly known until fixes are available that users can use to patch their systems. That way you minimize the risk that users will be exposed to bugs. So please follow this process if you discover bugs in the code and you want to report them. You can also use it if you find something in the code that looks suspicious, you're not sure, either you're not sure if it's really a security bug. So you can go through this process, and it means that you'll have someone to talk to, maybe it's the maintainer of the code, who can then help you figure out what's the severity of this, is this really a security issue? So that's the page to go to, and that's the thing to get started with. Now QEMU has a long history, and there's a lot of different use cases. People use QEMU in different ways, and those different ways have kind of different expectations, different security requirements associated with them. So I have basically the most trivial example here, toy kernel development. Say you want to do a bit of low-level programming, you want to play around with operating systems concepts, so you're hacking on your toy kernel and you want to test it and run it inside a VM, so you use QEMU. In that case, the virtual machine, the guest, is trusted, right? Because it's just running your code. And chances are it's not even connected to the internet, so the risk of anything malicious coming from that guest is basically non-existent. In this scenario, the user is also trusted because it's just you. You're not going to try and hack yourself. There's no real issue here. But in most real-world use cases, we do have components that are untrusted. So what I want to do is I want to first go over what QEMU's security requirements are, what the QEMU community today agrees on are the security boundaries, and I hope that that will help you when you evaluate your own use case and you think about, is it safe for me to use QEMU? Because you basically just need to make sure that what QEMU guarantees is at least as strict as what you need, right? If you have stricter requirements than what QEMU guarantees, then you need to either talk to the community and see how you can get QEMU to fulfill those stricter requirements, or maybe you need to consider an alternative and not use QEMU. So how does that work, right? We're an open source project, we're a community. So how do we decide what the security boundaries are? Because there's different, like I mentioned, there's different use cases. Someone might use QEMU as a research platform to prototype things, or want to share their experiments with the community. And so they might just want to commit code, get it merged, and share it with people, but that code isn't really hardened. It's not something that you would want to deploy in production, where there might be malicious users who would want to compromise you. On the other hand, you might have people who say, well, I need an emulator or a hypervisor that has very stringent, meets very stringent security requirements, and I really don't have time for any of the other stuff, the features that I'm not using, and so on. So you have kind of a spectrum of different, where you could be on this spectrum. And the way it works is because QEMU is a project, as people join and leave the project, the focus shifts around a little bit, and it has shifted over time. And so basically what I'm saying here is I'm just encouraging you that if you find you have stricter requirements than what QEMU currently supports, there's always scope to enhance QEMU and discuss it with the community. If you have very few requirements, then it's going to be hard to convince people that they should run an insecure QEMU. So it's hard for us to go the other way, but we can sometimes make it stricter if it becomes clear that there's demand for that. Okay, so what does QEMU do today? Today, for the virtualization use case, and there I mean using KVM, the guest is considered untrusted. The guest is considered, it could have malicious code. It could be trying to compromise the rest of the system. The user-facing interfaces, like VNC, for example, they are also considered untrusted because those might be given to untrusted users who will then connect to the VM. The network protocols, basically talking to anything external, is considered untrusted. And the same thing for user-supplied files, like disk images or kernel image files and those things. QEMU doesn't trust them. So that's virtualization. But for the non-virtualization use case, which is TCG, that's when you're not using KVM and you're using the software just-in-time compiler. At the moment, there are no security claims. There are no kind of guarantees on security support. The reason for that is largely historic, because a lot of that code is the oldest code. Some of it doesn't get used very much, or it gets used in use cases where you don't have security requirements. Or it's unaudited. So at the moment, that stuff is not considered kind of a security boundary. But this changes over time. So if the community, if people do decide it's time, we need to support certain things, then the effort can be put in, and these guarantees can change. And this is also documented on that same security process wiki page that explains how to submit security bug reports. Okay, so one thing we don't have, though, which would be very useful, is a per feature list of the status, whether features are considered safe for production. It's not that people don't know this. People do know what's safe and what's not. So QEMU does have some experimental features in it that you shouldn't really deploy in production. But the problem is today, it's really downstreams that know that and that have that knowledge. And we don't have a single table or page on QEMU.org where you can go to and say, oh, I want to use this feature. Is it supported? And I think we can fix this problem. And basically, today, it's the package maintainers, Linux distros, or organizations that build QEMU from source and use the binary who decide which features to build in and which features not to configure into QEMU at build time. So I think we need to get this information upstream. It'll make it much easier for newcomers to see, okay, maybe I shouldn't touch this feature because it's something that's experimental. It's not suitable for production. Okay, before I move on to the technical parts, are there any questions about the process and about the things I've talked about so far? Okay, so I'll move on to kind of describe the architecture. So we're going to look at the virtualization use case, right? Because the non-virtualization use case doesn't have any security claims associated with it. So for virtualization, what you have, just as a refresher, the overview is that you have a management tool that orchestrates the VMs. So it starts them, it stops them, it live migrates them, and so on. And then you have one QEMU process per virtual machine. Inside QEMU, you have the guest branch. And QEMU also handles most of the device emulation. So it contains the device emulation code. And this code gets triggered, it gets called when a guest tries to access hardware registers on its device. It traps into QEMU, QEMU is able to emulate that. Okay, and then QEMU itself doesn't run the guest instructions. The guest CPU instructions, they get executed by a driver, like KVM. And basically what that does is it switches the host CPU into guest mode so it can safely execute untrusted guest instructions. So there's that driver component inside the host kernel. The other piece that's inside the host kernel is that there are a few in-kernel devices. So I said that device emulation happens in QEMU, but actually there are a few exceptions. Usually these exceptions are for performance reasons, or they are because the kernel has certain in-kernel APIs that are not available to user space, and it would just not be possible to get that functionality from user space, so we have to do it inside the host kernel. Okay, so those are the components that we have, and I'm going to be focusing on QEMU today. Okay, so in the title of this talk, I mentioned isolation. I mean, this is the key thing. How do we isolate the guest? And I'm going to go into a few of the aspects of isolation now. So first of all, we want to make sure that whatever is running inside a virtual machine cannot escape, cannot compromise the host, cannot gain control of the system. It's always going to be stuck in its virtual machine. So the guest has a few attack surfaces for escaping into QEMU. The main one is device emulation, because your guest has a certain set of emulated devices, and whenever it writes to hardware registers, that traps into the device emulation code in QEMU. So if there are any security bugs in there, that might be a way for the guest to gain control over the QEMU process. And just a reminder that that QEMU process is running on the host, and it's a user space process there. TCG, of course, is another attack vector, but I'm not really going to go into it because it's not covered by the security guarantee. Only the virtualization stuff is currently supported for security. Okay, so what other aspects of isolation are important? Well, a guest must not be able to attack another guest. The traditional attack vectors are always going to be there. If you have the IP address of another guest, and it's running some network service, and you can connect to it, then of course, if it's unpatched or whatever, you can still exploit it. So the traditional stuff is not what I'm talking about. What I'm talking about are virtualization-specific attack vectors. So you do have one here. What if you manage to get control over QEMU? Can your QEMU process go and attack other QEMU processes? We need some isolation there. Otherwise, once QEMU is compromised, it's game over, and all the other VMs are also compromised. So that's very important. So I'm going to talk about how that's achieved. And the final aspect, maybe this should have been the first one, because it's a very critical one, is these in-kernel devices, or drivers, right? The KVM kernel module and anything that's running in the kernel. That's the most privileged part of the entire system. And if that is compromised, then your entire host, including all the guests, are also compromised. So that's the most security critical part. In this presentation, I'm mainly focusing on QEMU, though. I'm not going to go into KVM kernel module specific things. So I've given an overview of the architecture and talked about isolation. So the next step is to kind of talk about what the security design is, how things work. So one of the main properties that we have in KVM is defense intent, because we already have this virtualization stack. We already have multiple components. We have the management tool, we have QEMU, and then we've got the host kernel components like KVM. So it's important that if one of these components is compromised, it doesn't give you access to the entire system. Compromising one component you get access to that component, but you'll have to find additional attacks to get into other components. And that way, a single compromise isn't enough to reach your goal as an attacker. It makes things harder for attackers to have multiple security boundaries. So this is a pretty well-known thing, and just due to the architecture of KVM and virtualization, we're able to take advantage of that. So I want to highlight that, but I'm going to get into some of the specifics now. So how is the QEMU process isolated? So the management tool, this is not QEMU, by the way. This is not the QEMU program. When it starts up, it does a bunch of magic stuff. Instead, this is something that the management tool needs to do. And this is something that libvirt specifically already does today. It's really important to run QEMU as an unprivileged user. And that might seem obvious, but it's often tempting to run QEMU as root if you're giving it access to some devices, like some network interfaces or something. Because if you run it unprivileged, what you have to do is you have to launch it unprivileged, and then you have to send it the file descriptors to just those few privileged devices, or those few network devices that you want to give it. So sometimes people say, oh, that setup this is too hard. I'm just going to launch QEMU as root, give it the path to a network interface. That's a really bad idea, because remember, if QEMU gets compromised, then the attacker would actually have root on the host. So it's very important to run QEMU unprivileged. But you can go beyond that. I mean, being an unprivileged user is not really enough, because if you have two processes from the same user running on the same UID, they can still interfere with each other. They could maybe p-trace each other, or if you're using Unix file permissions, they could access the same files on disk, which you don't want. You want to isolate the disk images that are assigned to each guest. So guest A cannot access guest B disk. So one way of doing that is using SE Linux. And so libvirt implements this. So there are a bunch of things it will do to actually confine the QEMU process and ensure that even if the QEMU process were to attempt to open the disk image, for example, of another VM, then it will fail because SE Linux will prevent it. And the same thing about ptrace. I mean, debugging, if QEMU were to ptrace another process, that will also fail. And the final thing here is resource controls. If libvirt configures resource controls on QEMU, then they're enforced by the host kernel. And so gaining control over QEMU will not allow you to escape. You'll still be stuck with those resource limits. So that's another important factor to have. So always check that your management tool is doing this, especially if you run QEMU, if you launch it manually, or if you use a custom tool, because you may be missing some of the stuff. And if you do that, then in practice your actual security will be worse than if you say used libvirt. Okay, so let's move on to the next kind of design idea that's important. So every single virtual machine has a single QEMU process dedicated to it. So it's a one-to-one thing. One VM belongs to one QEMU process. And what that means, what we can do is we can give that process only those resources that belong to the VM. That means the disks, network interfaces, graphics cards, whatever. QEMU should not have access to anything else, anything beyond that, because otherwise if QEMU is compromised, you will gain access to those resources that you shouldn't have access to. So if we can do this, if we can strictly give only the privileges that are needed to the QEMU process, then what happens is when you break out from the guest into QEMU, you haven't gained very much because you just have access to those same resources. Now, you use the native APIs, you use syscalls to access those same resources, but you haven't gained any other resources that you shouldn't be allowed to access. So this is a very important principle. The problem is that this is just theory, because in practice, in the Linux user space environment, it's actually quite hard to confine things to that extent. So in reality, the guest compromising QEMU will gain a few things that it could use to then further attack the host. The most obvious thing is the system call interface, right? So you're no longer inside the guest, you're now in the QEMU user space process. You can do any system call that you want to. So any of these kind of native APIs are now available. And in order to prevent that and mitigate that, both SE Linux and seccomp can be used. So libvirt also supports seccomp. Seccomp is actually set up by QEMU when it starts up, so it's a little bit different. It's not externally set up. But what it does is it can blacklist certain system calls. System calls that QEMU should never, under any circumstances, use. And so you can at least reduce the kernel attack surface. You can at least get rid of some system calls, and you can be sure that a compromised QEMU cannot make those calls in those kernels. There's actually a whole talk on it. So if you're interested in that aspect on seccomp, you can check out Eduardo's talk. So basically what he goes into is that, again, it's kind of this theory versus practice thing where it's very hard to confine the QEMU process all the way down to the theoretical minimum that you would like. So he goes into that a little bit more. Let me give you another example. If you're wondering, so what else do I gain if I break out into QEMU? If you're using network storage and you're using QEMU drivers, so say you're using Ceph, for example, and you're using QEMU's RBD driver, then there will be a file descriptor and an IP address for talking to whatever server the Ceph client is talking to. So now that you've escaped, you can also talk to it. And imagine that on your Ceph deployment, you've got lots of other disks, all the other guests' disks. When you were inside the guest, you only had, say, a VirtIO block device. you had no way of enumerating or even getting to all those other disks. But now that you've escaped into QEMU, you have the ability to connect to Ceph. And you could try to look at other disks. So the best practice here, in order to mitigate this and prevent any issues with this, is to always use authentication if you're using network disks. Because you basically have to assume that your VM eventually would be able to just connect to the server and try to gain access to any LUNs that you have there. So you can do that with iSCSI, you can do it with Ceph. It's possible to put passwords on and so forth. But that's a very important thing to realize. Okay. So the final thing is that, unfortunately, some of the resource limits that we offer, like block I/O throttling, they are implemented inside the QEMU process. So if you compromise QEMU, you can bypass them. So suddenly, you're no longer limited to whatever it was, 50 megabytes per second disk I/O bandwidth. You can now just skip that because you've compromised QEMU, and you have access to that disk file descriptor. And there are solutions to that as well. For example, you can use the kernel block I/O controller, and libvirt supports that. So that's one option if you're not using a network storage. If you're using network storage, you could see if the server side supports rate limiting. If it's very critical for security that people don't abuse, don't break those limits. So this whole thing about the principle of least privilege, in theory and reality, I think is quite important for developers to understand. Because as we add new features to QEMU, we should always keep in mind, am I giving QEMU access only to the resources that belong to the guest? Or am I giving QEMU access to something else? QEMU shouldn't be enforcing anything. QEMU shouldn't really be the last line of defense, preventing the guest from gaining access to something. So we need to give it as little as possible. And if there are exceptions for practical reasons like what I've described, documenting them is the most important thing so that people, when they deploy it, are aware of the security impact. Okay, so we've talked a bit about the design and the general architecture. I'm going to move on to the next section now. Did anyone have any questions or comments on what we just talked about?
One small comment. You say there is defense in depth, but unfortunately that of course doesn't apply to KVM. It's in the kernel, and if you find a vulnerability in KVM, you remove it.
Yeah, so Paulo mentioned, I'll just repeat the question. So Paulo said that defense in depth works for the QEMU process because it's a host user space process. And there's additional layers that we can still have in between.
No, I meant exploiting the KVM API
yes.
from QEMU.
I'm getting there.
Okay. Yeah, okay.
So then the point is, if you go and you attack the KVM kernel module directly, and you gain access to it, there are no more layers of defense. You're already in the host kernel. So this is the most security critical part of the system, and we don't have additional layers of defense there. One thing you can do, though, is I mentioned in-kernel devices. vHostNet is the most well-known one that people use. Now, depending on how paranoid you are and how important this is, you could opt to not use that device because typically we also have a user space implementation of that. And so that user space implementation will probably be a bit slower. These devices are usually there for performance reasons. But you'll have better security because now you have defense in depth again. So that's a choice that you can make.
Yeah, and you can exploit KVM both from the guest or through QEMU.
Yes. Yes.
You can exploit KVM without breaking in QEMU.
Yes. So there are some interactions, obviously, that the KVM kernel module has with the guest. But there are also some interactions using IOCTLs that the QEMU process has with guests. So actually, there are two separate attack surfaces there.
Or three if you get a multiple execution in QEMU.
Yes.
I think we should add another thing that once we should add another thing. Once the real physical device is passed into the guest, the security model is completely changed.
Okay. Yeah. Yeah. So if you use device pass-through, then of course that has implications because you no longer have a software layer that is mediating the access and limiting things. Okay, so I'll move on to the next section. For the next section, I want to go a little bit more in depth, and what I did to start this is I went and looked at the security history of QEMU. I looked at the security bugs that have been reported. I looked at the severity and what the cause was. And I want to kind of highlight a few, and then we can go into discussion on what it means. One of the well-known ones, VENOM, came out a few years ago. It was a bug in the floppy disk controller emulation code. I think the reason a lot of people got scared is because the floppy disk controller is there by default in a lot of machines. And so everyone's like, oh, I'm not using this, but it has a security bug, so this is a bad thing. How do I get rid of it? The actual bug itself was a typical C programming bug. It was a heap buffer overflow. And it's guest triggerable, because this function here, the FD control write data function, gets executed when the guest writes to a hardware register on the floppy controller. And what was happening is that there were some floppy controller commands that never reset the array index data pos. And so if you just keep calling them, you would be able to overflow the array, and then you would be able to write to memory beyond the end of the array. So potentially you could then get code execution if maybe there was a function pointer or something like that beyond there. So this kind of leads us on to what are the important things for device emulation code? Either because you're reviewing it or you're auditing it for security, or because you're a developer and you're emulating a new device. So I'll go through some of the things that I think are quite important. So sadly, number one, C programming bugs. If you look at our CVE history, a lot of them are buffer overflows, integer overflows, use after free, these kinds of typical C bugs. So that's the number one thing to still watch out for. Number two, this one is obvious, is that we don't trust the guest. So it's important to validate all inputs. As an example of this, say you're emulating a device that has 4 execution units, and it has a hardware register that lets the driver select which unit you're currently talking to. So QEMU should never trust that number. It should always validate to make sure it's only 0, 1, 2, or 3, one of the 4 units. It shouldn't just index into an array, because then the guest could put in a bogus number and you'll go beyond the end of the array. So we always have to validate inputs from guests. This is very widely known, so when there is a bug, it's typically because this is like the one case that was forgotten in this device. But let me move on to some more interesting ones, to some more subtle ones that are not so well known. When you implement device emulation, it's usually understood that there's a certain order in which the driver will do things in order to do its business. So in order to send packets, or in order to update the frame buffer, or whatever your device does. However, as a driver writer, you can kind of stick to that. You'll just initialize the device in the way that the hardware specs recommend you do it, and so on. But as an emulation author, you can't rely on that. You have to anticipate that any possible hardware register on your device could be accessed at any time, even at times where it doesn't make sense for them to be accessed. And they could be accessed in the wrong order as well. So malicious guests could try to trigger bugs in your code. So one example for this would be if you have a device that takes a request, some kind of I/O request, and then that request is pending for a couple of milliseconds or whatever, and it expects an interrupt. Well, during that time, what happens if the device already starts writing to the registers again and gives you another request? You need to make sure that your device emulation code doesn't corrupt whatever is in progress, doesn't leak the pending thing, right? You need to basically make sure that the state machine, all possible transitions are covered. So this one is really hard to find with source code analysis tools like static scanners, because they're mainly looking for C bugs. You're not going to spot this. So this is where human reviewers and auditing is very important. Another issue in devices is validating the live migration of the end state data that gets loaded. And historically, we haven't always done that very strictly. And then for reliability reasons, we've done it more, because if live migration is not working and you're having a really hard time debugging it, wouldn't it be a good idea to validate the inputs? And so over time we started to do that more. Turns out it's actually important for security too, because one scenario is someone might create a disk image file, make it available for download, and it contains a snapshot. And people want to load that snapshot, see what it does. Well, if a malicious user created this file, that snapshot could contain corrupt migration data, and you don't want it. You don't want that disk image restoring that snapshot to compromise QEMU. Another kind of subtle one, luckily our memory API is designed in a way so it's hard to shoot yourself in the foot here, and it happens rarely, but it does happen sometimes. It's just like in the kernel, in the syscall boundary, if in the kernel you can't really trust user memory, you typically would copy in what the user has requested from you if they give you a struct, and then you would process it, your own local copy. The reason for doing that is other threads could still modify that memory. We have the same thing in QEMU. When the device emulation runs, other vCPU threads might still be running. So if you fetch a field, and then you perform a check on it, you go do some other things, and then you fetch it again, it could have changed the second time you fetch it. And so they can bypass your check with a race condition. So it's important to copy in data from the guest. Do not trust guest memory. Okay, so I'm going to go on now to kind of security improvements and upcoming things that are happening. But does anyone else have any things they want to shout out and share? Something that I've missed here that is important when writing device emulation code? Christoph?
So it's not really for device emulation code, but you were mentioning earlier about things like accelerators, etc. So if at some point later we decide to have some of the management of SANs and devices in the guest instead of in the host, then you have also to add some security layer there. I don't think it exists today, but at some point this might happen.
So there are two things that can help with some of those things. One is actually related to users. It's building the source with hardening techniques like the control flow integrity, memory safety, maybe address sanitizer, fortify source. So that's something that users can do to harden the QEMU in general. And the second thing is fuzzing. It can help with invalid inputs and unexpected states. So is there any practice of using those things?
Yeah, so why don't I go to that section. So what can we do to improve QEMU security? I've kind of split this into three classes of things. One is finding bugs early. So you mentioned fuzzing. We have this device emulation code. But if what we do is we write the code and then we boot Linux or Windows or something and say, oh, it works great, my job is done, then we're missing a whole bunch of potential bugs that could be in that device. And so what fuzzing is about is random input testing. You send random inputs to a program and you see if they crash the program or get it to misbehave. And by doing that, because you're sending it random inputs, you're exploring the entire input space. So hopefully you will find crashes and issues. It's not done upstream, it's done downstream. So there are some organizations, some users of QEMU who have specific devices that they care about and they fuzz them. But we don't have an upstream fuzzing effort. I know that there is a Google OSS fuzz, and I think some people have played with it a little bit to see if we can hook into it, because then we get the compute resources to actually run fuzzing, and we could do it upstream. But that's kind of an open project if anyone is interested in doing that. So another thing is static analysis tools, and that's already widely used today. So there are static analysis tools that are being run on the QEMU code base to make sure that C programming bugs and things that can be automatically detected are being found. And then those bugs are being worked through and the patches get upstream. So that's working okay. Code audits, we have code review. Patches do not just get merged, there has to be at least one review, but oftentimes there are actually more than one review. So security bugs also get found at review, but there's no kind of formal auditing going on, especially not upstream. Okay, so that was how do we find bugs early. What about how do we mitigate the impact of bugs? Because just finding bugs is not enough. You're not going to find all bugs. So you need to also reduce the severity of bugs when they do happen. So that's what mitigating the impact of bugs is all about. I talked about sandboxing, so SU-Linux and Seccom, trying to confine the QEMU process so that the damage that can be done once you gain control is minimized. But those interfaces and the capabilities of those systems aren't perfect, so that continues to evolve. So if Linux gets new capabilities, hopefully someone can apply them on QEMU and jail and sandbox QEMU more tightly. One way of doing this might be multi-process QEMU, where instead of having a single QEMU process that is doing a lot of things, we have multiple processes, because then these multiple processes have specific tasks. And so the number of system calls that they require is smaller, and you have less problems confining this, the sandbox, basically. So that could improve things. We also have modules. So modular QEMU is something we've had for a couple of years now. It's not widely used yet, but the idea is when you build QEMU, you have a core QEMU binary, and then you have shared libraries for features, and they get loaded at runtime. Now, for security, the good thing about this is that if your process is compromised, the code footprint is smaller. And so it makes it harder to write certain types of exploits that reuse pieces of code that are already in memory. So by reducing the footprint, we make it a bit harder to exploit QEMU. QEMU historically also has been quite monolithic. We haven't always added features to compile out and disable things. So for example, now it's possible to disable TCG, but that took a long time. For a long time, you always had the TCG code in there, even if you weren't using it. So you can do this statically at compile time as well. And a lot more work is possible. So if people want to be able to build without certain features or devices, there are ways of doing it, and patches can be sent upstream to do that. So that was mitigating bugs. What about eliminating entire classes of bugs so that we don't even have these headaches and don't even have to worry about it? There are some things we can do here. One thing that always gets discussed is using a safe programming language or a safer programming language that eliminates some of these bugs. So Rust is the one that's been kind of most seriously discussed because it seems to have most of the qualities that we want. The challenge there is that we have a large code base, over 1 million lines of code, and so that's not going to migrate to a new language right away. Maybe the way to attack it is for us to start using the new language on new features, new processes that are separate from the original QEMU binary. Something we can do, though, which is a lot less impact and which will help, is to maybe restrict ourselves a little bit and not open code stuff in C when it's dangerous to do so. So for example, that FIFO, the floppy bug, if the author of that driver, of that device, had, say, used a FIFO API that had bounds checking and had checked for the size of the current pointer in the FIFO, then that bug would have turned into maybe a denial of service. It wouldn't have been code execution. It would not have been memory corruption, because we could have said, wait, your index is too big, there's a bug here, stop queuing it. So that doesn't totally eliminate it, but at least it avoids the worst problems that you get with certain aspects of the C programming language. So yeah, so these are some things that we can do. All right. I think I'll just see if there are any other questions.
I think you have missed an ability to whitelist some code or drivers, which is done in downstreams at least. I'm speaking right now about disk formats, virtual disk formats, which could be whitelisted.
So I'm not sure I understood. Could you explain again?
We have a code, for example, the realization of different virtual disk formats, and at least in downstream QEMU we have an ability to have some formats whitelisted, and they are not available. The blacklisted formats are not available in QEMU. Only whitelisted formats are available, but not whitelisted formats are used in QEMU IMG.
Okay.
This is also an ability to have some strength in not tested code.
Okay, thank you.
So you mentioned multi-process QEMU. Is that a thing, or is that just an aspiration?
It's multi-process QEMU is already a thing in the sense that vhost user exists today. So you can write VirtIO devices, VirtIO style devices or vhost style devices that live in a separate process. So yes, that exists, but it's the whole thing has been in active development over the past couple of years, and people are still working on new things in that area. So it's definitely not finished. You know, there's more to do.
And I think there was a good talk by Marc-André, I believe it was KVM Forum last year, or maybe DevConf, which talked about pushing some of the graphics components in a separate process. And Spice, for instance, is a relatively large piece of code, includes a number of components like GStreamer, etc. So in itself, it represents a relatively large body of code that is susceptible to bugs and so on. So putting that, it has absolutely no reason to leave in the QEMU process itself.
Yes. Okay, so I think we're now running out of time. Is there one more question?
Actually, I had two. One is if you need to share like a video device, like a camera, so how do you share device nodes? And second one, often you need to pass network connectivity. So how do you do some double IP tables on both the host and the guest, or can you make specific IP route bridging for the network?
The short answer for networking is that the configurations are actually very flexible. There's many ways you can configure that, and that happens outside of QEMU. That's something that either libvirt or you can set up manually. So you can use software bridge or whatever. There's many ways of doing it. So there's no one way. About the device pass-through, the camera. I mean, QEMU has PCI device pass-through, it has USB device pass-through, and you can do that. You can give a raw device to the guest, and the guest then just uses its normal device driver to talk directly to it. Could introduce new security issues, of course. So, okay, so I think we have to end here because we're running out of time. Thank you.